Why is Google JAX a threat to Nvidia? Executive Summary. Google JAX and its dedicated tensor processing units TPUs pose a substantial threat to Nvidia. Nvidia's power rests on its ubiquitous GPU hardware and the proprietary CUDA software ecosystem. JAX, a high-performance math library, combines with the XLA compiler to create highly optimized machine code. Google fully controls this vertically integrated software and hardware stack. This arrangement leads to superior efficiency and significantly lower costs for training massive AI models. JAX accelerates the industry's shift toward compiler-led optimization, directly challenging Nvidia's software lock-in and high profit margins. Article: Nvidia dominates the world of artificial intelligence. Its powerful graphics cards fuel most major AI systems. Researchers rely on Nvidia's hardware for large-scale training. Google now challenges this dominance with its own specialized technology. The threat is not just new hardware. It is a completely new software ecosystem called JAX. JAX works hand-in-hand with Google's custom chips, the tensor processing units, or TPUs. This combined approach gives Google a powerful, integrated advantage. It directly targets the massive market share held by Nvidia. Google effectively controls its entire AI stack. Nvidia only sells the hardware and its proprietary software. The confrontation between these two tech giants will shape the future of machine learning. Nvidia built its powerful empire over many years. Their graphics processing units, or GPUs, were initially designed for video games. Scientists soon realized GPUs could handle many parallel math operations. This specific capability makes them perfect for deep learning. Nvidia smartly developed a software layer called CUDA. CUDA allows programmers to write code that runs perfectly on their GPUs. This software created a vital advantage for the company. CUDA became the industry standard for all AI development. Developers and researchers are heavily invested in this stable ecosystem. This CUDA moat makes it very hard for competitors to convince users to switch. The entire industry currently speaks the language of CUDA. Nvidia controls the hardware and the necessary software. Google introduced JAX as a direct challenge to this status quo. JAX is a Python library built for high-performance numerical computing. It feels incredibly similar to NumPy, a common math tool for Python programmers. This familiarity makes JAX easy for developers to adopt quickly. JAX offers several key features that set it apart. It uses automatic differentiation for calculating gradients. These calculations are absolutely essential for training any neural network. Programmers can efficiently calculate the necessary changes. JAX also uses the concept of composable function transformations. This technical feature allows developers to manipulate functions in new, powerful ways. JAX represents a new approach to building and scaling machine learning models. JAX relies heavily on a technology called XLA. XLA stands for Accelerated Linear Algebra. XLA acts as a powerful compiler for machine learning models. A compiler translates human-readable code into efficient machine instructions. When a developer writes a JAX function, XLA steps in to optimize it. It converts the program into a highly efficient computation graph. This optimization process targets the specific hardware being used. The function runs much faster than standard Python code. JAX uses a just-in-time compilation process. This means the code compiles right before execution. XLA ensures the code achieves the best possible performance on Google's hardware. This compilation step gives Google incredible flexibility and speed. JAX includes several special functions that enhance its power. The JAX.JIT function performs the powerful JIT compilation. This step speeds up code dramatically. The JAX.grad function handles automatic differentiation easily. Programmers can quickly find the slope of a complex function. This specific operation drives all backpropagation in deep learning. Another function, JAX.VMAP, handles vectorization automatically. Vectorization means applying the same operation across a batch of data. This efficiently utilizes the parallel nature of accelerator chips. Finally, JAX features JAX.PMAP for parallel computing across multiple devices. Researchers use this feature to scale models across huge clusters. JAX gives developers elegant tools for building massive, high-speed models. Google's ultimate threat involves its proprietary hardware. The Tensor Processing Unit, or TPU, is a specialized chip built by Google. Engineers designed TPUs from scratch to handle tensor operations. Tensor operations form the fundamental math of neural networks. Unlike Nvidia's general-purpose GPUs, TPUs are application-specific. They perform specific tasks with extreme efficiency. This specialization makes them much more power-efficient. They also offer a better cost-to-performance ratio for large workloads. TPUs are not found in consumer PCs. They reside exclusively within Google's own massive data centers. JAX is the preferred language to speak directly to these specialized chips. The software and hardware work together seamlessly. Google controls the entire technology supply chain. This vertical integration creates a huge advantage. Google designs the chips and the JAX software. They own the data centers and the cloud service. This full control allows them to optimize the whole stack. Google can reduce the total cost of ownership, or TCO, substantially. This efficiency is hard for Nvidia to match. Nvidia sells chips to many different customers. Google only needs to worry about its own infrastructure. TPUs connect in massive clusters called pods. These pods use a custom high-speed network. This network enables excellent communication between thousands of chips. Vertical integration helps Google achieve superior scale and lower costs. The cost savings Google achieves are truly substantial. Experts estimate TPUs can offer 30% to 50% lower TCO per unit of effective compute. This significant saving becomes crucial for training massive language models. AI labs require billions of dollars in compute power. Google uses these TPUs to train its own flagship models, like Gemini. This internal self-reliance justifies massive investment in the technology. Major competitors like Anthropic commit to using Google's TPU infrastructure. This adoption confirms the viability and scale of the hardware. The low cost per operation is threatening Nvidia's high profit margins. Customers want alternatives to the expensive chips offered by Nvidia. JAX and XLA challenge the long-standing power of CUDA. CUDA represents a powerful software lock-in for Nvidia. Researchers and companies are reluctant to rewrite years of code. However, JAX makes the code inherently more flexible. JAX code can run efficiently on CPUs, GPUs, and TPUs. The OpenXLA project further pushes this hardware agnosticism. XLA strives to be a compiler backend for many frameworks, including PyTorch. If other AI frameworks easily adopt XLA, the CUDA advantage weakens. Developers would simply write their model and let the compiler optimize it. This shift moves power from the chip designer to the software compiler. The software ecosystem becomes hardware independent. Google JAX presents a powerful, coordinated threat to Nvidia. It is a new software stack paired with highly optimized hardware. Nvidia offers flexible, general-purpose GPUs. Google provides specialized chips inside a fully controlled cloud environment. Nvidia must innovate on both its hardware and software. They are responding by developing higher-level software like CUDAX. They also emphasize high-speed networking for their chips. The AI industry is currently growing at a rapid pace. This growth means there is room for both major players. However, Google's integrated stack offers a serious long-term challenge. JAX is accelerating the shift toward compiler-led optimization. This evolution could eventually dry up the deep moat surrounding Nvidia's lucrative business.